In this lecture, we're going to start a new topic today, which is the continuous time Fourier transform, or CTFT. In today's lecture, we're going to define the CTFT and give a few examples on how to compute the CTFT of certain signals. So the CTFT of a signal x of t, which is a continuous signal, is defined as follows. The CTFT is denoted by xj omega, and it's the integral between minus infinity and plus infinity x of t e minus j omega t dt. So you could probably notice certain analogies with this transform with other transforms that you've seen before, such as the Laplace transform, or even you can think of it as a generalization or the equivalent transform of the discrete time Fourier transform. And the inverse Fourier transform is given by the following expression. So it's x of t. So given xj omega, the CTFT, you can recover the original continuous signal x of t by the following formula. Before we go further, just a few remarks about notation that you're probably familiar with. So the continuous signal x of t, we will denote it by using a lowercase symbols. So it could be x of t, y of t, or h of t. And sometimes the CTFT xj of omega is referred to as the spectrum of the signal x of t. It's an analogy that comes from comparing the signal to light. For this reason, for example, when you're analyzing noise, you hear expressions such as white noise or white Gaussian noise. Also, like I mentioned in the definition, the CTFT of the signal is x of j omega. From a mathematical point of view, it's weird that you have this constant j here. So it's basically because the CTFT is a function of omega. But we just write x of j omega, and this is in this way just to, I think one purpose of it is that when you see it, you immediately know that it is the CTFT of the signal. So if you see x of j omega, you know it's the CTFT of a certain signal. Also, one more remark about the definition and the assumptions that we make here before we proceed to examples. So, in the definition, the CTFT was defined as a function of the angular frequency, omega, which is in radians per second. And you could also define the same, the equivalent CTFT as a function of the frequency f, which is, the unit of it is hertz. And the relationship between omega and f is that omega is equal to 2 pi f. So for those of you who remember physics, you probably remember this this connection. And then if you want to express the CTFT as a function of f, then this would be the formula, which is obtained by the simple change of variable. So you just apply this change of variable to the definition, and you get this this connection. Now, when you express things in frequency, the nice thing is that the inverse Fourier transform, you lose the 1 over 2 pi here, so it's just easier to, you don't have that extra factor here. So, but usually in signal processing, we will, most of the time we use the omega, but in communications, when we're applying these concepts in communication, we tend to use more hertz. And you would hear, for example, of let's say like 3G is over this and this bandwidth in hertz, and this signal should fit in this bandwidth, and so on and so forth. Let's do one example. An example one here is to find the CTFT of the following complex exponential or exponential signal e minus at uta, where a is greater than 0, and the signal here is drawn for a being a real number, but a could be any complex number. Now, to find the CTFT of the signal, all we have to do here is just to apply the formula, and you've seen the signal many times before, or this kind of family of signals. So once you do the integral, so this is the integral of e minus at ut e minus j omega t dt, And then because you have the step function u of t, so this is a right-sided signal, so this kills everything that's in the negative part of the axis, so your integral now is from 0 to plus infinity. And you club together e minus at and e minus j omega t, so you get this function here, dt. And therefore, when you do the integral of the exponential, so it's going to be the exponential divided by the term here. And then you plug in everything, so for t equal to 0, this is going to be equal to 1. So you're going to get the term minus 1 over a plus j omega, so this is y plus 1. And for infinity here, this term is going to go to 0, because e minus infinity, the limit is 0. So what you should remember here, and this is really, this could be very useful in general, is that to remember the CTFT of a right-sided exponential, so it's x1 of g omega is equal to 1 divided by a plus j omega. Now, many times it helps to see the CTFT in a graph or pictorially. So how can we see it? Because it's a complex function. So what we will do, we will plot two things. We will plot the magnitude and the magnitude here of xj omega and the phase of xj omega. So here the magnitude, because it is x1 of, in this particular example, since x1 of j omega is 1 divided by 1 plus j omega, we know that the magnitude of x1 of j omega is equal to 1 over the magnitude of a plus j omega, and this is going to give you 1 over square root of a square plus j square, plus omega square. And then the phase is going to be equal to the minus the arctangent of omega by a. And then what we do here is we draw the magnitude and the phase on two separate graphs. And usually the magnitude is going to be interesting because it tells us, we're going to talk about the examples of filter design. It tells us which frequency, if this, the signal is actually the impulse response of a certain system, it tells us which frequencies the system cuts and which frequencies let go through. But for now, what you should keep in mind is that the CTFT is a complex function, and to represent it pictorially, we'll need to represent its magnitude and its phase. Let's do now example 2, which is, if you think of it, it's the left-sided version of the previous signal. So it's x2 of t equal to EATU minus t. So it's, if you think of it, it's the reflection of the previous signal across or over the y-axis. So the previous signal, maybe if I draw it here, the previous signal was this. So this was x equal to what we just did before, e minus at ut. So we're doing the symmetric of it here. And I'm not going to do it in details because these are the same steps. And in the end, you get the following CTFT of the signal, which is 1 over a minus j omega. And also, it's helpful to keep these formulas in mind. I mean, if you also forget it, that's fine, because you can easily derive it. Now, examples 3, maybe it looks a little bit more difficult or more involved. It says the question is to find the CTFT of the single x3 of t here, which is e minus a, the absolute value of t. Now, what is the signal equal to? If t is positive, right, the absolute value of t is equal to t, and x3 of t is actually e minus a t. If t is negative, then the absolute value of t is equal to negative t, and x3 of t is equal to e minus a minus t, which is e minus, or e plus at. So what it gives you, so for positive t, it's e minus at, and for negative t, it's e minus a plus at. And what that gives you, it tells you that for positive t, this signal x3 of t is equal to x1 of t, which we did, and for negative t, x3 of t is equal to x2 of t, which is also we just found the CTFT of. So what you can write, we can write that x3 of t is equal to x1 of t plus x2 of t. Since x3 of t is equal to x1 of t plus x2 of t, using a linearity of the CTFT, which I didn't prove it, but you can easily check it here, meaning the CTFT of the sum is equal to the sum of the CTFTs. So x of g omega is equal to x1 of g omega plus x2 of g omega, and then we just found these two values here, so it's 1 over a plus j omega plus 1 over a minus j omega, and then once you find the common denominator, you get x of j omega, which is 2a divided by a squared plus omega squared. So this would be x. This is actually x of 3j omega. So here should be 3.